And maybe we can start.
Okay.
Yes. Hi, everyone. So welcome back to the second talk in this series. Today's speaker is Stephen Simon from Oxford University. He's going to talk about a general solution of the Kitaev quantum double model. Steve, if you're ready, go ahead anytime.
Okay, thanks. So as I was saying just a moment ago, I'm really thrilled to be giving this talk because there aren't a whole lot of audiences in the world who find this super interesting, but I find it super interesting, and I'm hoping that you guys will too. So this this work is based on mostly one paper, but also two earlier works with a group in Paris, Anna Ritz-Zweiling, who is the first author and the graduate student who did a lot of the work, and Benoit Dussault, Julien Vidal, and Jean-Noël Fuchs. And this was a really fun project that we worked through, and I'm going to tell you about. So before going on, I want to have a shameless promotion, which is to read my book. So I put out this book in Oxford University Press, Topological Quantum. It is really aimed at physicists, not mathematicians, but I've been told by a lot of mathematicians that it's actually quite useful to understand how physicists come at this problem. And it introduces ideas of anyons and topological quantum computation and TQFTs from a condensed matter theorist perspective. The book is not incredibly cheap, so I will forgive you if you don't actually buy the book. But if you don't want to buy the book, there's a free draft on my website, and the free draft parts of it are very similar to the book. There's some chapters in the books that aren't in the free draft at all. But conversely, there are some parts of the draft that aren't in the book at all because the book was just getting too long, so I had to cut it off somewhere. So there's the parts of the draft on the website that people might be interested in. There's a large section on fractional quantum Hall effect that basically didn't make it into the book at all. So if you're interested in that, you can also read that in the draft on the website. I should also say, if you're please do feel free to interrupt me and ask questions and slow me down if I'm not being clear. If I don't make it to the end of the talk, that's fine. If I make it only a third the way through, that's probably still okay. All right, so the outline of the talk, I'm going to first introduce the Kitaev quantum double model, and then I'm going to give the fairly simple quote general solution of the model, meaning tell you what all the eigenvectors and eigenvalues are of this Hamiltonian, and see that the solution is actually fairly simple, but the derivation of it is actually pretty tricky, and that's going to, if we have enough time, occupy most of the next hour and a half. But it's okay if I don't make it to the end of that. Probably more interesting just to get through the first two parts. So let's start with this. The Kitaev quantum double model was introduced by Kitaev in his very first paper on topological quantum computing. This is the paper that, as far as I can tell, really started it all. In 1997, Kitaev realized that anyons were interesting for topological quantum computing, and he understood the relationship between topological order and quantum error correcting codes. I was told to make this fairly pedagogical, so I don't know how much people know about this, but again, please do slow me down if I'm speaking gibberish and you need things explained. None of it is extremely difficult, but if you haven't heard some things before, they may seem rather obtuse. Anyway, in this original paper, Kitaev introduced the toric code, which is really the it's like the hydrogen atom, the simplest model of topologically ordered matter. And I think when people talk about topologically ordered matter, what they always have in their mind is the toric code, is the simplest possible model. The toric code also can be thought of as a TQFT, or it can be thought of as a quantum error correcting code. And it's not really just a a toy model. It's actually genuinely the best quantum error corrected code we know of by a lot of measures. When all these quantum computing companies like Google, like IBM, like Quantinuum are trying to build error-corrected qubits. What they're actually trying to build is the toric code. That by many measures, the toric code is the simplest, easiest to implement, most efficient error-correcting code that we know of, and it still seems to be the one that everyone is trying to do. But in addition to introducing the toric code, he also introduced a more general model, which we now call the Kitaev quantum double model, which also is a TQFT, which is the quantum double of a group. So the group is, we call G. The quantum double of the group we call Z of G. That's a particular TQFT. Sometimes people call it D of G for double. And the thing that Kitaev pointed out was interesting was that the Kitaev quantum double model, if you start with the right group, you can construct this microscopic model, which would give you anyons which are computationally universal by braiding and measuring. So you braid the particles around each other and you measure them appropriately, and you can do universal quantum topological quantum computation. So this was, as with many things that Kitaev does, it's way ahead of its time and introduced new, completely new ideas, completely revolutionized the field. Now, the quantum doubles was something that people had thought about before. If you have a discrete group, a finite group, and you build a 2+1 dimensional lattice gauge theory out of it, what you get out is a quantum double as a TQFT resulting from such a construction. This was first discussed, I think, by Drinfeld in 1987 in a language which is probably much more familiar to everyone in the audience than it is to me. I find it very hard to understand this paper. But then in the 1990s, particularly work with Sander Bias and Mark de Wilde-Propitius, and also by Loan Preskill, they reconstructed these quantum double models in terms of things that physicists understand. What are the particle contents? What's their fusion properties? What are their braiding properties? And things like that. And then it became something that physicists were interested in studying. There's one more early work that I'm going to point to quite a bit, which is work by Gould from 1993, which worked out some of the representation theory of the quantum doubles. And that actually ends up being, I was not actually familiar with this work until I went looking for it. For this particular project, I figured someone must have done this work early on. It turns out it was Gould. And it's important for the calculation that we end up doing. Okay. So some information about quantum doubles. What you put into this, you can think of a sort of a quantum double as being, I don't know, a black box. And you put into the black box a discrete group. You choose your discrete group and you put it in. And the thing that comes out is the quantum double out Z of G. So you pick your favorite group, S3 or A5 or whichever, monster group if you're really adventurous. And this quantum double is a 2+1 dimensional TQFT. You can think of that as an anion model or a modular tensor category. I realize not all TQFTs are modular tensor categories, but this one does happen to be a modular tensor category. And the anion types, or so-called simple objects of the modular tensor category, come in various classes. One class is known as the fluxes, and those are labeled by the conjugacy classes of the group G. Then there are the charges, which are labeled by the irreducible representations of the group G. Then there's the dions, which are labeled by a conjugacy class and an irrep, but not an irrep of the group G. Instead, an irrep of the centralizer of a representative element of the conjugacy class. So first what you do is you choose a conjugacy class, then you choose a representative element of the conjugacy class. It doesn't matter which one you choose. And then you look at the centralizer of that representative element, all the things that commute with that element. That forms a group. And then you look at the irreducible representations of that subgroup. And that gives you the set of dions. So it's a somewhat complicated set of constructions, but it's well known how to construct all the details of this TQFT, of this modular tensor category. You can calculate all the Fs, all the Rs, all the thetas, the twist factors, anything you want about this TQFT is well known by this time. If G, the group, is nonabelian, then the quantum double of the group has nonabelian anyons. Okay. So actually, maybe I should ask, are there any pressing questions already? Is everyone happy so far? Okay, so far so good. All right. All right. So for the Kitaev model, we're going to construct the model. We have to define it first. And the first thing we have to do is we have to make a Hilbert space. So to make a Hilbert space, the first thing we do is we choose a two-dimensional manifold, and let's just choose it to be orientable and without boundary. So it's just described by its genus G. So it's a couple comments here. First of all, it's easy to define the Kitaev model with a boundary. I'm just not going to do it here, but it's not that hard a generalization. For some groups G, you can work with non-orientable manifolds, but it's not generic. Usually you can't. So let's assume we have an orientable manifold. The other thing I'll comment is that for genus, I'm going to use this calligraphic G because I want to preserve the normal font G for something else. So my genus is calligraphic. So let's choose some manifold. We're going to describe it with
Steve.
Yep.
There is a question from the chat. Are you working over the real or complex numbers?
It will. Okay. I'm not sure. I believe it's going to be complex. The Hilbert space will be defined with complex numbers. Where did I use anything so far that would? I don't think I have yet said anything that would where I have to make the choice yet. Is that correct?
Yes.
With the
okay.
irreps. Oh. With the irreps. Complex. Yeah. Sorry. Thank you.
And the manifold is compact, yes?
The manifold is compact. Yeah.
And may I ask a question while we're paused here?
Yeah.
You mentioned that for certain G, you could define the model on unoriented surfaces. Do you have a characterization of which G you can do that for?
The answer is certainly known, and I think it's cases where each
I've been wondering about this lately, so maybe I'll just ask you later.
No, it's definitely known. It'll take like just a second of thinking. You need I think everything has to be. There's a paper by Barkeshli that works this out in a great amount of detail, actually.
Really? Okay.
And so for example, the toric code you can do. The toric code doesn't need to be orientable, but you need to be able to. I think maybe that restricts it to just. Oh, was that? Maybe that just restricts it to Z2 to a power or something. But I'm not sure. I haven't. It's definitely known, but I don't know it offhand.
Okay, I'll bug you for a reference later. Yeah.
Okay.
Thank you.
Yeah. Okay. Yeah. You're welcome. Good. Thank you for the questions. I like it when it's interactive. Okay. So we're going to take our manifold. We're going to define it with, the usual way. We're going to divide it up into faces, which I'll also call plaquettes, edges, and vertices. I guess mathematically you call this a CW complex. Here's a picture of a two-handled torus divided up into plaquettes and edges and vertices. This picture actually isn't generic because if you look at it closely, you'll notice that every single plaquette has 4 edges. That's not required. It's just I couldn't find a nice picture that didn't have this property. So this is the nicest picture I found. Of course, we have the Euler characteristic equation that probably everyone learns in high school. 2 minus 2 times the genus is the number of faces minus the number of edges plus the number of vertices, which we're going to use. Something that I didn't realize is that this was well known before Euler. Just one of those cases where the wrong person gets credit, apparently. Okay. So now we're going to define our Hilbert space, and we are going to do so, we orient each edge. So we put an arrow on it. Doesn't matter which way the arrow points. The Hilbert space assigns an element of the group to each edge. So, this edge is labeled by a group element G12. This element is, G9 and so forth. Every single edge gets a group element. And the most general vector in our Hilbert space, or general wave function, if you're thinking as a physicist, is just tensor product of all the edge labels. So G1 is the group element on edge 1, G2 is the group element on edge 2, and so forth up to Gn. Some complex coefficients here, arbitrary complex coefficients, and you sum that up over all group elements, and that gives you the most general wave function that you can have, and that then defines your Hilbert space. Good. One more thing, that if I reverse my arrow, I should interpret that as inverting the group element. So it's equivalent to put an arrow going up with a label G or going down with a label G inverse. Okay. Oh, the Hilbert space dimension. Actually, do you see this little thing blocking the picture, or is it just me who sees this thing blocking the picture?
No, not at all. I think it's fine.
It looks fine? Okay, good. So the Hilbert space dimension is just the index of the group, the number of elements of the group, to the power of the number of edges. However many edges you have, each edge has, GL, capital G, different choices, and so the Hilbert space dimension is G to the E. Good. One comment for those people who've seen this model before. So Kitaev defines his model in a particular way, and I'm going to define an equivalent model, but on the so-called dual lattice. Now, first of all, I realize that this is not what a mathematician calls a lattice, but physicists insist on calling it a lattice. We would call it a disordered lattice, which I know is not a lattice by mathematical standpoints, but ignore that. It's whatever it is. Here, the Kitaev's lattice and my lattice are going to be dual to each other. In other words, if you here, so this plaquette is plaquette labeled 1, and over here it's going to be a vertex labeled 1. So plaquette 1 is separated from plaquette 7 by an edge labeled G17, and over here vertex 1 and vertex 7 have are connected together by an edge labeled G17. So it's just that over here, the vertices would be where the center of these plaquettes are. Now, if you've never seen the model before, this is not going to bother you. We're just doing it. I just write down my lattice. If you've seen Kitaev's model before, you're going to say, why are you doing that? You're calling a plaquette a vertex and a vertex a plaquette. So this picture in the middle has both of them. Here's my lattice in blue and Kitaev's lattice in black. There's a reason why I'm doing this different from Kitaev. Kitaev wanted his picture to look like a lattice gauge theory. I want my picture to look like a string net. And they're absolutely equivalent in every way. It's just a lot easier to make my arguments in terms of a string net than it is in terms of a lattice gauge theory. Although in our paper, we actually go back and forth. Most of our paper, if you read the paper, is actually in Kitaev's convention rather than in my convention, but okay, this is what I'm going to do, so bear with me. And if you've never seen it before, it's not going to bother you. If you've seen it before, it'll probably drive you crazy, so I apologize. Okay, good. So I'm now going to define some operators on my Hilbert space. The first operator is going to live on the vertices, and this operator is going to check that the group multiplication around the vertex is going to multiply up to the identity. So however many edges are coming, we're going to orient all the arrows pointing out from the vertex. So this is vertex alpha. This happens to have 3 edges pointing out from it. And what we're going to do is we're going to go around the vertex in a clockwise manner and multiply together the group elements, G1, G2, G3. And if those 3 multiply up to the identity, this operator gives you the value 1. And if it doesn't multiply up to the identity, you get the value 0. Okay, so this is a projector. Obviously, v squared is v. If there were 4 edges coming out of the vertex, it's you just multiply all 4 in a clockwise manner going around the vertex as well. Okay, this is this operator is enforcing some sort of flux conservation. If you think about sort of group valued flux coming in or out of a vertex, it's the total flux coming in or out of the vertex has to be the identity in some sense. Okay, that's the point of this operator. Okay, people happy with that? Yeah. Okay, good. Okay, the second operator I'm going to define is an operator that that acts on a plaquette, and it has a parameter here h. And the point of this operator is going to pre-multiply. I'm going to orient all the edges in a counterclockwise direction, and this is then just going to pre-multiply all the group elements by h. Okay. Obviously, these operators follow the group multiplication law. They're a representation of the group multiplication, because p of h followed by p of h prime is the same as p of h prime. Now, this operator, what we're going to use it to build something else. We're going to build a bigger operator, which is going to sum over all possible values of h in the group of this pre-multiplication. And the point of this is to enforce some sort of gauge invariance around the plaquette. We're going to pre-multiply by all group elements, and then we're going to average over all of them. Okay, it's easy. It's pretty easy to show in about 2 lines that this is also a projector. If you square this operator p beta, it also gives you back p beta, just coming from this law. And so this operator is here to sort of check gauge invariance. Now, what's maybe not obvious is that the plaquette and all these operators commute. Plaquette operators commute with plaquette operators. Vertex operators commute with vertex operators. What's maybe the least obvious is that the plaquette operators commute with the vertex operators. So here's a vertex operator. Here's a plaquette operator here. And to convince yourself that they commute, what we'll do is at the vertex, what the vertex operator is doing is it's trying to enforce. Well, I'm going to start the. Okay, maybe back up. I neglected to say something important here. That when I try to figure out if G1, G2, G3 multiply to the identity, it actually doesn't matter if I started at G1 and went around, or if I started at G2 and went around, because if G1, G2, G3 is the identity, then also G2, G3, G1 is the identity. So it doesn't matter where I start. So here I'm going to start at G3 and go around. I want a G3, G1, G2, but I need to have all the edges pointing outwards. So the condition here is G3, G1 inverse G2 should equal the identity. That's the condition at vertex alpha. Then I'm going to imagine pre-multiplying the plaquette around all these elements going around the plaquette, pre-multiply by h, and then consider the vertex condition again. So G1 here gets pre-multiplied by h, G2 gets pre-multiplied by h, but then when I invert this, the h inverse gets moved to the right, it then cancels the h here, and it preserves this condition. So pre-multiplying the plaquette by h doesn't change the operator at the neighboring vertex. So that's basically telling you that the plaquette and vertex conditions are commuting with each other. Okay. So this brings us to the actual Hamiltonian that we're going to consider. And the Hamiltonian is just a sum of all these commuting projectors with minus signs. There's a sum of the vertex operators with a minus sign, the sum of the plaquette operators with a minus sign. These operators, they're all projectors. They have 2 eigenvalues, 0 and 1. And the ground state of this is going to have to be when all of these operators are in the +1 eigenstate. This thing is basically a discrete lattice gauge theory. Where maybe I should say this, that the plaquette is enforcing gauge invariance, and the vertices is enforcing this flux conservation at the vertices. So there's gauge invariance of the plaquettes and flux conservation at the vertices, or flatness. You can think of this at the vertices. What's interesting about this model is that violations of gauge invariance are allowed, but they cost you energy. So if P beta is not in its +1 eigenstate, it means you've broken this gauge invariance. In a lot of models, you say breaking gauge invariance is just not allowed at all. Here, it's just costs you sort of an energy penalty if you break gauge invariance, if you want to think of it that way. You can write down the ground state wave functions for this model, or the TQFT vacuums. And the way you do this is you start with any state you like, such that all the vertices fuse to the identities. That's would be what we call a string net. So the fusion at all vertices, the group elements fuse to the identity at every vertex. And then you start with that, and then you apply this P of H that pre-multiplies going around the vertex by a group element to H, and you sum over all possible H and sum over all applications of P of H over all the plaquettes, and sum up the results, and that gives you a wave function which is definitely in the ground state space of the TQFT. If you want to use this Kitaev quantum double model as an error correcting code, these are kind of the check operators that you're in the code space if all of these P's and V's are in the +1 eigenstate, and you're out of the code space if one of them is not in the +1 eigenstate. Any excitation of this model is where either the plaquettes or the vertices are not in the +1 eigenstate. If the P's are violated, that gives you what we call a charge, or a representation of the group. And if the vertices are violated, it's a net flux, and that's described by the conjugacy class. So since the time that Kitaev introduced his model, there have been over 300 archive papers with the word Kitaev quantum double in the Hamiltonian. Google Scholar gives it 700. Not sure which one is right, but it's a lot of papers. And it actually took 29 years before we had a complete solution of this model, and that's what I'm going to describe to you. So maybe I stop there and ask if there are any questions before I move further. So that's the model.
Okay, so I guess so right now, if anyone has any question, feel free to unmute yourself and ask. Maybe I can first start with a question. So here, I guess you haven't defined what is an anion excitation, or do you call any excitation an anion excitation?
Right. So that's right. I mean, for my purpose, so far for my purposes, I haven't needed that. What I'm going to do is I'm going to find all of the eigenstates. Actually, I'm going to do more than that. I'm going to generalize this model first before solving it. But what I'm going to do, I'm going to find all the eigenstates, all the eigenvectors, all the eigenenergies of this model. And I don't need to, in principle, I don't need to know anything about anion braiding or anything like that to do so. But it will turn out that there will be obviously an intimate connection between the fusion properties of the anions that you would get out of the quantum double and the details of the solution of this model.
Okay, so I guess the eigenvalues are not I mean the eigenvalues, like you have the ground states, and then for every excited states, they jump like for every time, for every excited state they jump by 2 or 4.
Yeah, but in this case it's defined to be 1. But okay, for each plaquette or vertex that so far for each plaquette or vertex that's violated, it's 1. But of course they may have to be violated in pairs, for example.
Okay.
So
thanks.
you're right. For the, yeah, so toric code, they typically use +1 and -1 eigenstates instead of 0 and 1. But it's, you can switch from one to the other if you want. Good. Oh, there's a hand raised from Matthew.
Yes, thank you. So if this is pure gauge theory, is it possible to couple matter to that kind of system? And if yes, how to proceed?
Yeah, so I think, okay, it's in some ways you want to think about the violations of the flux conservation as being sorry, the violation violation of the flux conservation as being matter. However, you have to be a little bit careful with doing this because this is a model where gauge invariance is not an absolute statement. Gauge invariance is something that you're allowed to break here. So it kind of doesn't fit into the, I mean, I think this is why it took so long before someone wrote down this model, because it seems like you're doing something that's very unnatural by allowing gauge invariance to be broken.
I see. So matter is actually already present in some sense, like
Yeah,
when you violate the flux conservation, I guess it corresponds to some electric.
I think that's correct. Yes.
I see.
Yeah.
So is there such a thing as a pure gauge theory then?
Yeah. So if you wanted to have something as pure gauge theory, you would enforce the gauge conservation condition absolutely. You would fix it as part of as a definition of the Hilbert space.
Oh,
you would say that. Yeah.
Not as a Lagrange multiplier in some sense, but you wouldn't.
Yeah, you would have to make sure that that you cannot access the violations of gauge invariance.
Okay, thank you very much.
Yeah, good. All right. So before going on, I want to.
There's a question in the chat. Sorry.
Yeah. Okay.
There's a question. Do you have dions in the picture?
Yeah. Okay. So this is interesting. So let me just say a couple words here before we go on. Thank you for the question. Let me say a couple words because it's exactly what I'm going to talk about next. Okay. So this is an important advance from 2017, which from Anna Komar and Olivier Landon Cardinal. I haven't met either of them, but I get that it was Caltech and Quebec, and they pointed out that anions that are dions are sometimes not energy eigenstates. In principle, the anions are there as far as some of the topological properties of the model. That if you make some anions, say that happen to be energy eigenstates, and you fuse them together, you can get out a bunch of different topological sectors. But if you try to pin down the energy eigenstates, you will discover that some dions are never energy eigenstates of the model. And that's actually, I mean, in some ways it's actually going to be obvious that this has to be true. But it was a little bit surprising. I think this is one of the reasons why people didn't actually go ahead and solve this model for a long time, because it looks unnatural. And let me say a little bit more as we go along, and you see how the solution works. You'll see why the dions, they're there as part of the topological structure of the model, but they're not there as part of the energy structure of the model. So, and the thing that one of the things that these people did, which was really useful, is they generalized the Hamiltonian a little bit more. And by generalizing the Hamiltonian a little bit more, which you would think makes things more complicated, it actually clarified a lot. At least to me, it did. So I'm going to go ahead and do that. All right. What's going on here? Here. Okay. So yeah. Okay. So first thing I'm going to do is I'm going to generalize the vertex operator. So these are going to be, I'm going to turn them from something that just looks for flux conservation at the vertex that forces you to fuse to the identity. Instead, I'm going to allow it to fuse to anything you want, but with various energy penalties. So in Kitaev's model, he just says, okay, if you fuse to the identity, you get negative energy 1, and if you fuse to anything else, it's energy 0. So here I'm going to let those any I'm allowed to fuse to any conjugacy class I want. C's are conjugacy classes, and they get an energy penalty E sub alpha comma C. So alpha is the name of the particular vertex. It can be different at different vertices, and each conjugacy class at each vertex, it can be assigned whatever energy you want them to be assigned. Just some list of how much energy you charge particular conjugacy classes at particular vertices. Okay, so this is generalizing in a huge amount. You can pick them to be the same from vertex to vertex, but you don't have to. You can choose, like Kitaev did, that all the conjugacy classes except the identity cost you the same amount of energy, or you can make them all cost different amounts of energy. Okay, so that's the first thing we're going to do. The second thing we're going to do.
Sorry, one question. So in the previous slide, so for each vertex is different.
Yeah.
You have alpha 1, alpha 2 for each vertex, yes? And then also you have different conjugacy class also in each vertex?
Yeah, so I have a list of conjugacy classes. Say my group has 3 different conjugacy classes. I can assign the 3 different conjugacy classes different energies at different places in the system. So for each vertex, I can assign the 3 different conjugacy classes different penalties if I wanted to. I could choose them to
But do you want, for example, connect vertex alpha to vertex beta?
G1 so G1 will connect alpha to beta, yes. But the conjugacy class is a property of G1, G2, G3 here.
But is there any extra condition that is between the conjugacy class of each vertex then? If G1
No,
is part
they can be completely free. Even 2 vertices right next to each other, I can choose the energy penalties to be different, right next to each other in any way I want. Okay. Then I'm going to also generalize the plaquette operators. So instead of just summing over, so this P operator is the one that pre-multiplies by a group element H going around the vertex. Instead of just adding up these pre-multiplications by H, I'm going to add them up weighted by group characters. So chi R is the group character of representation R with dimension D sub R within the group G. And if I weight all these, weight the sum over the group with these representations, I get a set of orthogonal projectors. So these projectors satisfy a nice orthogonality condition for representation R prime is delta R prime. So that's nice. And then what I can do is I can make a full plaquette operator which applies an energy to each different possible representation I can have on that plaquette. And they don't have to be the same at different plaquettes either. I can choose energy penalties for different representations in different places. Now what Kitaev did is he said, if you're in the identity representation, the trivial representation, you have low energy. And if you're in any other representation, you have energy 0. And when I say, well, let's give all representations any possible energy you want. And you can make them different in different places too, if you want. Okay? All right. So this seems like, then we write down exactly the same Hamiltonian. It's just the sum of vertex operators and plaquette operators. It's still a sum of commuting projectors, but now it's assigning different energies to different charges and different fluxes in different places. Okay. So, having generalized the model, now we can write down the general. Yes.
Steve, so in your Hamiltonian, are those terms the same as before, or are the new terms?
These are now the new ones. These are now, So this new Hamiltonian has these vertex operators that allow different weightings at different penalties at different positions, and new plaquette operators so the vertex operators allow different penalties for different conjugacy classes at different vertices, and the plaquette operators allow different penalties for different representations at different positions.
Okay, are they still like a commute with each other exactly? Because
they still commute with each. Yeah, that all the representation operators commute with all the They all commute. They all definitely commute with each other, independent of the weightings.
Okay.
Independent of what you choose for the energies, they all still commute.
Okay. Yeah.
Okay. Yeah.
Yeah. Thanks.
Okay. All right. So, what's the solution? Surprisingly enough, this intermediate part of my talk is only like 2 or 3 slides long. So, the full solution. Here's my Hamiltonian. The solution goes as follows. For each vertex, you assign a conjugacy class to it, and you give it the appropriate energy. For each plaquette, you assign a representation to it, and you give it the appropriate energy. And if you've chosen a representation R, you have to choose a vector within a d sub r dimensional space, where d sub r is the dimension of the irrep R. Okay? These states that we just constructed have energies given by the sum of all the assigned vertex and plaquette energies. And this should be kind of obvious. These are all mutually commuting projectors. You can choose independently at each vertex exactly what conjugacy class you have, independently at each plaquette exactly what representation you have. And each of them get the appropriate energy penalty and the appropriate representation penalty. Okay? That's part one. Maybe not so obvious is that there's an additional vector of dimension d sub r associated with the representation R that's sitting there as well. So there's an additional degeneracy sitting here. So far, so good. That's part one. Having chosen these conjugacy classes and these representations and these vectors within the space of the representation, actually, maybe I should say that it's maybe not so surprising you have to choose a d sub r dimensional vector because you've chosen a representation of a finite dimension. And so whenever you choose a representation of a finite dimension, you have to choose the vector that you're considering within that representation as well.
Is this representation a representation of the centralizer or
No,
just a group?
no, it's a representation of the group. Representation of the group, not the centralizer. The centralizer is almost not going to play a role at all, as you'll see. That's the surprise. The dions kind of don't play a role. They're not energy eigenstates. They'll play a role only in the topological properties of fusion within the space, but they don't play a role in the eigenspectrum.
Okay. Okay.
Which is really kind of surprising, but that's how it works. So we're choosing the conjugacy classes, the representations of the groups, and then these vectors. And then, having chosen those, you have to put a Wilson. You have to choose a Wilson line going around each handle of your manifold. So if you have genus G, you choose one anion quantum number from the quantum double, from the Z of G, the resulting TQFT, and you put that around each handle. Okay. Given these choices, there is now a topological degeneracy of the eigenstates. So we've as soon as we chose the C's and R's, we've fixed the energy of the system. There's a degeneracy of small d sub r associated with the representation of finite dimension. But then there's in addition a topological degeneracy given by the fusion multiplicity, the number of ways that all the fluxes and charges and chosen Wilson lines around the handles fuse to the identity within the quantum double. So you take these are all objects within the quantum double. These are fluxes, pure fluxes. These are pure charges. You fuse them all together, and you fuse the Wilson lines around the handles. Fuse them all together, and they have to fuse up to the identity. And that's the topological degeneracy of the eigenstates that you have just found. Now, I should contrast this with the degeneracy associated with the dimension of the representation. That degeneracy, there's an additional degeneracy associated with this D. You're choosing a vector in this space. That degeneracy is non-topological. And when I say topological versus non-topological, what I mean is the following. If I take Kitaev's Hamiltonian and I perturb it with some local terms that add energies associated with whatever you want, any local term, any local Hamiltonian term with a small coefficient, so it doesn't completely ruin the system. The topological degeneracy is not broken, that it will stay exactly degenerate, but the degeneracy associated with choosing these vectors in the space is broken by local perturbations. Okay, so this representation degeneracy is breakable, but the topological degeneracy is not. Okay.
There's a question, what is the Anyon quantum number?
Right. So when I say Anyon quantum number, I mean you choose a simple object from the quantum double Z of G. Choose one simple object from that. That when I say Anyon quantum number, I just mean the name of a simple object. It's hard to change your nomenclature on the fly. So I use terms that condensed matter theorists would understand, and I they're so deeply ingrained in my head, I don't realize they're not obvious anymore. So I apologize. So, okay, good. Other questions? Yeah. Was there one?
No. Okay.
No?
Yeah, very good.
Okay. So if you sum over all the possible A's and all the C's and all the R's, then and you fuse them together on a so yeah, okay, so right, okay. Let me restate this. If I just look at this equation here of I'm fusing together a whole bunch of fluxes and a whole bunch of charges and all of these quantum numbers associated with the Wilson lines, the problem of summing all this degeneracy over the A's, if I just sum over the A's, that gives the pure TQFT, if I just describe the TQFT Z of G, and I ask what is the degeneracy of the ground state with a bunch of C's and R's fusing together on a genus G surface. So these A's are doing nothing surprising. This is exactly what you do if you had any TQFT and you put a bunch of objects on the surface of your system and you ask what's the degeneracy of your system now, given that you're on a system with a non-trivial genus. Okay. That might look familiar to some people. All right. So one thing we should check is that if we sum over all of these choices, sum over all the fluxes, all the charges, all the D's, these vectors in this space, and all of these the Wilson lines going around the handle, we should recover the full Hilbert space dimension, because we then should have summed over every eigenstate in the system. So let's first do this problem of summing up a bunch of fluxes and a bunch of charges. These are objects of the quantum double on a genus G surface. And this is sort of a classic problem in TQFTs. You have, you sew together a bunch of Pants diagrams with fusion multiplicity matrices within the quantum double. You use the Moore-Seiberg-Banks formula or the Valinda formula. The earliest place I saw this formula was in the Moore-Seiberg paper on the conformal zoo, but they actually credit the formula to Tom Banks, so I call it the Moore-Seiberg-Banks formula, which tells us the degeneracy of these fluxes and charges fusing together on a genus G surface is given by this sum, all x's in the quantum double. These are the modular S matrices. This is a sum over all of the C insertions, and this is the sum over all of the R insertions. Sorry, product over all the C insertions, product of all the R insertions. That gives you the total degeneracy. Okay. Does this look familiar to some people? Hopefully. Yeah. Okay. Good. I see some people nodding. Okay. So then this looks terrible. How am I going to get anything out of this? Well, there's two nice identities that the S matrix has two eigenvectors with eigenvalue 1, call them NF and NC. And NF is a vector which is 1 if X is a conjugacy class or is a pure flux. And n sub c is a vector whose value is the dimension of the representation if x is a pure representation or a pure charge and 0 otherwise. Now we can use these to if we're going to sum over all the conjugacy classes, we're exactly doing this sum here, and it will destroy all these, get rid of all these s's, and just give us a delta function with only where it's only non-zero if x is a conjugacy class. And similarly here, if we sum over all possible representations, including the dimension of that representation, which we need because we have this choice of vectors in the representation, this will also kill these S matrices here and leave us only with the appropriate dimensions. But this then gives us x as being non-zero only for x equals I. This thing restricts you only to conjugacy classes. This thing restricts you only to representations. And the only thing that is both a conjugacy class or a pure flux and also a pure charge is the identity. So the whole thing collapses to the total dimension. The total dimension of the entire system is the identity S matrix element to the 2 minus 2g minus vertices minus faces. That's the total quantum dimension of the system to this power, and the total quantum dimension is just the index of the group, so it gives us the index of the group to the e power using the Euler characteristic here. So this whole complicated formula collapses, and when you sum up over all choices of fluxes, all choices of charges, all choices of vectors in the representation space, and all Wilson lines around the handles, you end up getting the full Hilbert space dimension. So that works out well. So these two identities, I invoked them without explaining them, but they're actually, these identities are really crucial identities for discussing modules of the quantum double model, or edge structures of the quantum double model, or the kind of condensations you can make for the quantum double model. Those are all equivalent. And this one tells you that you can have, it's basically telling you can have what Kitaev calls both hairy edges and smooth edges, and both of those can be gapped. So these are these conditions actually have physical meaning besides just being pulled out of thin air. Okay. So are there any questions so far? Okay. All right. So that's basically the answer. That's the fairly simple solution. And you know, I think if I conveyed this much, since I've used up an hour, if I conveyed this much, I'm pretty happy, because you know, this is the fairly simple solution, and the derivation of it is, you know, it gets a little complicated in places, but that's what's coming next. So if there are questions so far, ask now. Otherwise, I'll move on to what the solution is.
Steve, there's a question in the chat. I'll just read it out. Can you say a few words how you detect the topology of the underlying manifold from the Hamiltonian or the solution?
Right. When you say topology of the manifold, do you mean the genus in this case, or do you mean some? Yes. Okay, so let's back up. I think, yeah. So I'm not sure. I mean, the yeah. So you're saying if, I mean, in some ways, I think it's okay. So if someone hands me the system, the first thing I would do is you could if you look at the full solution, the first thing you know is the you know the dimension of the Hilbert space, right? And if you know the group that you put in, you know the dimension of the Hilbert space, so you know the total number of edges in the system immediately without doing anything else. right? Because that's just going to set the dimension of the Hilbert space. Then the question is, can you look at, so for example, if someone handed me the spectrum, if someone handed me the spectrum, what's the quickest way I could find of determining if what the genus was? Let's see. I think most. I'm not. Okay. I don't think I have a slick answer. There's enormous amount of information in the in the system, and from the Hamiltonian, I think it's sort of if someone gives you the Hamiltonian, they had to give you the genus first, because they have to tell you where all the edges are and how many vertices you have and how many plaquettes you have and things like that. But if someone, I think maybe an interesting question is, if someone only gave you the eigenspectrum, just the energies, could I extract the genus just from knowing the energies and the degeneracies? And there I'm not sure. I mean, maybe if someone told me the group and gave me the eigenspectrum, I'm not. I kind of think you should be able to do it, but I'm not positive. So I don't know. I don't have a great answer for that. I'm sorry.
Yeah, Steve. I think if you can vary the group, then probably can tell, and then combining with the degeneracy, you can probably tell the genus. But if you fix a group, then I'm not certain.
Oh, okay. So someone just linked someone example. Okay, I'm not sure I'm going to be able to read it in real time, but example 8.9 does answer it to some degree, assuming you know the group but not the manifold. I think if you told me in addition that the Hamiltonian was uniform, it's the same on all vertices and the same on all plaquettes. So I'm not doing this thing where I make the energies different on each plaquette and on each vertex. I think I could then do it pretty easily. But if you don't know that, I think it might get harder. So I'm not sure. But let me think about it. I think I bet there's a way to do it. I just don't have it offhand. So apologize. Okay.
Sorry, I have another question.
Yeah.
Could you also give maybe some comments about the relation of the model you explained with the CFT, with 2D CFT?
Yeah.
I know this Seiberg-Moore functor also exists to prove Berliner conjecture and in Liouville theory, but I cannot really connect that background with this yet.
Yeah. So for each TQFT, for each unitary rational TQFT, CFT, there's a corresponding TQFT. But I don't know whether the analog goes the other way. I'm not sure whether there's a TQFT. Just because so I have this quantum double of a group TQFT. I'm not sure there's a CFT that corresponds to it. I mean, the Moore Seiberg-Banks formula is a general state. Although they were thinking about CFTs, it's general and works for the same reasons for TQFTs. But I don't know whether there necessarily has to be a CFT corresponding to this TQFT. Yeah, I mean, I don't know what it is offhand, I think.
And even we cannot guess if such a CFT exists. Is it in like discrete spectrum or the continuous? It is like WZW type thing or Liouville with a continuous spectrum. Even we cannot have that information.
I don't know. I mean, it doesn't. It's not. I mean, it's not one of. Yeah, I mean, I think the quantum, let's see. So it would have to have, it's sort of, okay, if there's one that fits, it would have to have central charge 0. And that's already problematic from the standpoint of a CFT. And it's not, so yeah, I really don't know that there, what you can, I mean, yeah, I plead ignorance of this, so.
Okay, no, thank you.
Yeah, okay. Okay. So let me try to explain the solution here a little bit, or at least tell you what some of the tricks are. So how to prove the full solution? Well, to a physicist, you might get away with saying, well, it's got to be right because what else could the answer be? I mean, the solution is actually, it ends up being quite simple in some ways because it matches a bunch of conditions that you might be concerned about whether they could possibly be all satisfied at the same time. So one of the things is you know that each conjugacy class has to cost you a certain energy. Each representation has to cost you a certain energy. You have to have the representations have to act on some dimensional Hilbert space. You know that if you had no defects, if the conjugacy classes were all trivial and the reps were all trivial, you would still have the degeneracy of the manifold due to the Wilson lines around the handle. All these things have to add up, and the full Hilbert space dimension has to add up to the total number of degrees of freedom in the system. So all those things have to work. So what else could it be? But if you wanted to actually derive the results or produce explicit eigenfunctions, then you actually have to do a calculation. So we do the calculation in the paper. We do the calculation in two different ways. One way is from a lattice gauge theory perspective, and the other way is, quote, through lattice manipulations. And this is the one I'm going to discuss. But for those of you who like lattice gauge theory, I recommend you read the other one as well. And they're quite different from each other. Two approaches and to get the same answer, which is quite nice. I should say this is an AI assisted publication because everyone's talking about AI these days. I used AI to typeset my handwritten notes. It's actually quite good at turning. My handwriting is terrible, and nonetheless, it turned my handwritten notes into LaTeX pretty well. So I'm really impressed with that. And I did try feeding this problem to ChatGPT a year and a half ago, and it got absolutely nowhere on it. It made no progress whatsoever, and I was very disappointed. But it's gotten so much better. I'm wondering if I had waited a year and a half and fed it to it now, it would be able to make progress. But all right. So the big simplification we're going to use is lattice surgery, and the statement about lattice surgery is that there are basically lattice or surgery moves such that the spectrum of H on one lattice is equal to the spectrum of H on a second lattice. So I can change the lattice without changing the spectrum at all. And there's an exact mapping of the eigenstates, the eigenvectors on lattice 1 to the eigenvectors on lattice 2. So for example, I might make a surgery move on my lattice that takes a picture that looks like this and turns it into a picture that looks like this, keeping sort of the endpoints fixed and just changing the connectivity. And it's actually pretty easy to prove that this has to hold in the following way. So to prove this, I'm going to define a non-violatable vertex. And I'm going to define that by drawing a green circle around the vertex. And when there's a green circle around the vertex, it's going to imply that the edges impingent on the vertex multiply together to the identity. So in other words, it's in the Kitaev ground state there. And then once I have defined this non-violatable vertex, it's pretty clear that I can make these moves in the following way. So here I'm fixing the group elements A, B, C, D on the outside edges here. And then this internal edge X here is completely defined by A and B because this vertex here is non-violatable. That X has to equal AB, or it has to equal DC inverse. Either way, X is completely defined by A, B, C, and D. So in fact, you can just get rid of X completely. It's not any new information. There's a complete isomorphism of wave functions on this lattice to a wave function on this lattice. You just throw away X. It hasn't given you any more information. It hasn't given you any new degrees of freedom. It hasn't changed the dimension of the Hilbert space. Similarly, I could open this up in this direction and insert the edge labeled Y. But Y, since this is non-violatable and this is non-violatable, A and C have to multiply to be, or C and A have to multiply to give you Y, as do B and D inverse have to give you Y. And so Y isn't a new degree of freedom either. It's, it hasn't increased the size of the Hilbert space. It's not a new degree of freedom. It's completely defined by the degrees of freedom that are already there. So I can certainly take a picture that looks like this way over here on the left and turn it into a picture way over here on the right, as long as the vertices are non-violatable. Is that good? People happy with that? Yeah. Okay. So the second move I'm gonna, yeah.
Sorry, but I think I agree. For ground states, you can do this. But what about excited states?
Yeah.
Because the vertices are violated.
Okay. So let me introduce this. And so the non-violatable vertices are not going to be. Let me do this for a second, and then you'll see why I'm doing it this way. Okay. Just bear with me for 1 second. Okay. So the second move I'm going to do is the following. Here's my regular vertex, my violatable vertex. And I claim that this picture here, which is a vertex with 3 things coming into it, is equivalent to having a non-violatable vertex here and move the violation here. So why is this so? Well, here, A, B, and C, they don't have to multiply to the identity here. They multiply to some, non-trivial conjugacy class here, or non-trivial group element here. But I can just create this edge Y here and put the violation at this point instead of the violation at this trivalent point. So here, the conjugacy class at this point here, which is defined with outgoing arrows, so it should be A inverse, B inverse, C inverse, is the conjugacy class here, is still the same as the conjugacy class here, which is A inverse, Y inverse, or A inverse, B inverse, C inverse. So all I've done is I've taken the violation, I've moved it away from this trivalent vertex along to this bivalent vertex. And if I have if I have an excited state which is excited at this vertex, I'm free to move that violation over to here. Okay, and I haven't added any degrees of freedom, and I haven't changed the energy of the system in any way. I've just changed the picture. Okay, does that make sense? Yes, thumbs up, thumbs up. Everyone happy? Okay, so using these moves together, I can do the following. So here's 2 violatable vertices. Then I'm going to move the violations away from the edges, from the vertices here. So now they're on these bivalent vertices. Now I have 2 non-violatable vertices. I can switch the geometry to this, and then I can move the violations back on. So now this picture here is mapped to this picture here, and I've changed the geometry. But I've made an isomorphism of the wave functions. That the eigenstates here are mapped directly onto the eigenstates here, 1-to-1. Okay? Yeah? Does that make sense? Yeah? Okay, good. All right. So then you can you play this game as much as you like. You can change the structure of the lattice in all sorts of crazy ways. You can change a picture like this to this. You can change a picture, you can add a non-violatable vertex for free. You can add lots of non-violatable vertices and all sorts of things that you want. So the things that remain is there's always an isomorphism of the wave functions, and the eigenspectrum remains unchanged. So the eigenvectors are mapped by an isomorphism, and the eigenspectrum remains completely unchanged. What remains unchanged is the number of violatable vertices, and that has to be true because each violatable vertex has its own Hamiltonian. It has its own energy penalties, and so the number of violatable vertices has to be exactly the same in after every change of the structure. The number of plaquettes has to be the same. Again, each plaquette has its own Hamiltonian, And so we better not change the number of plaquettes. The genus of the manifold has to stay the same because we're making local moves, and you can't change the genus, global genus, with local moves. But we can still make lots of changes. So why don't we just choose a really super simple lattice, a really simple geometry where we can basically solve everything. So what's the geometry you want to choose? So for a sphere, this is a pretty simple. It may not be unique, but this is a pretty simple geometry. So I put all my violatable vertices in a line. All these other vertices are non-violatable. All my plaquettes are here at the end of the end of these lines. There's here, you'll notice I have the number of vertices are 1 up through number of vertices here. The number of plaquettes is 1 up through the number of plaquettes minus 1. Why is that? Well, because there's one more plaquette, which is the remainder of the sphere. So you draw this picture on one portion of the sphere, and then the remainder of the sphere, including the point at infinity, is the last plaquette. Okay? So I can use these local moves, restructure the lattice as much as I want, and then I turn it into this picture, which is a pretty simple picture. So far, so good?
So you can change any lattice to this one of this type?
Any lattice can be turned into this, yes. As long as its genus G equals 0.
Okay.
For a finite genus, or non-zero genus, I then have to have overcrossings and undercrossings. So this is basically my two handles of the torus. This would be the two additional handles of a two-handled torus. This would be, additional handles of the G-handled torus. So I would add these other things over here for a higher genus with overcrossings and undercrossings. And it's about the simplest thing I could come up with, which still describes a decomposition of genus G. And you notice that all the violations of the vertices are sitting right along this one row, and everything else is non-violatable. So I'm not going to do the finite genus case because it gets kind of sloppy, but I can probably do the genus G equals 0 case fairly quickly. So I'll try to do that. I realize I'm running over a little bit. So if people want to say, let's stop there, I got the idea, it's okay. But I can do a little bit. So we're lowering the bar a little bit. We're going to try to prove the solution on a sphere, G equals 0. And the idea is we're going to assign, the same thing. We assign a conjugacy class to each vertex, a representation to each plaquette. We have to choose a vector within a d-dimensional space. I have to explain to you how that's done if I want to get an explicit wave function. And given these choices, there's a topological degeneracy of the eigenstates given by a fusion multiplicity. There's a number of ways that the fluxes and charges fuse to the identity within the quantum double. So these are objects of the quantum double, and they're all fusing together to give the identity. Okay, so this is the geometry I want to use. And one thing that's really nice about this geometry is that a lot of the edges have to be the identity. Why? Well, let's look at this plaquette here. This plaquette here has a G coming out here, some group element coming out here. The same group element, oops, back up. The same group element, it comes out here and comes back in here. So that means this edge, this long edge, is the identity. So we can just erase it. So it can look like this. It just has this one long row of violated vertices, and then this set of n-1 plaquettes. So far, so good. We're almost there, actually. So what we can do is we can independently choose the group elements along this row, and that sets the conjugacy classes of these violated vertices. And we can independently choose the representations on these simple loops, and that sets the reps on those plaquettes. The thing that's non-trivial is the last plaquette. So the whole shooting match comes from the last plaquette, which then sews everything together and forces fusion to the identity of the whole thing. So that's kind of the interesting part. So remember, the last plaquette is this plaquette that goes around everything and encompasses the rest of the sphere, including the point at infinity. So that's the last plaquette operator. What do we do with that? Well, Okay, so here we're fixing the y's, the group elements along these edges to fix the conjugacy classes. Here, to fix the representations along these loops, I actually can write out explicitly the, so this row is a representation matrix, unitary representation matrix of the dr dimensional representation R. So for each of these plaquettes, I define the vector R n comma n prime, which is just the representation matrix summed over the group elements G with an appropriate normalization. And I can use basis wave functions, which fix the group elements along these edges and fix the representations along these loops. And this is an eigenstate of every single term of the Hamiltonian except the last plaquette term. So we're almost there in that we've solved the entire Hamiltonian except for one plaquette at this point. So the last plaquette, it needs to sew everything together. So this thing, when we, can break that up into this is one group element H, but these things here are in the identity. So we can sort of pinch these off, make it look like this. So it's H running around all of these plaquettes, H running around all of these edges like this. Applying H then mixes up all of the elements in this basis as I just defined. So I have this basis wave function which fixes the group elements along here. It fixes the representations along here. And then I apply this last plaquette operator, and it's going to mix up the elements of those bases. And the idea, okay, in a particular way, a particularly simple way. So when I apply this pH operator, which applies the last plaquette Hamiltonian term, it takes y's along these edges and it conjugates them by H. And it takes these representations along these plaquettes and it multiplies them by a representation matrix. Now notice that the representation is unchanged, so the representation is fixed. Each of these representations is completely fixed, and it's not disturbed by being multiplied by H on the outside. There's two indices of this representation. Let me show the representation matrix. The definition of this representation matrix has two indices, R n and n prime. One of these indices is completely fixed. It's not disturbed. This n is completely fixed and is not disturbed by being multiplied by H. And the other one is multiplied by a representation matrix. So this m is multiplied, but n is fixed. So this actually goes along with what we knew, that you choose a rep and a vector that's n here. And then the remaining topological degeneracy comes from these guys, these representation matrix, and these guys here. So is this getting too obtuse here, or are we okay still? Too obtuse?
I'm fine.
Sort of. It's fine. Okay.
At this point, it was like when you delete the edges, it's no longer a proper CW complex. Yeah.
No, it's the edges are still there. They've just been forced into the identity.
But I mean, the last face, it is not a circle. It is not a disk. It has punctures.
So here, okay, here it's a disk.
Yeah.
Yeah, here it's a disk. Here it's a CW. It's fine. And then here I'm saying, well, look, this guy here, it's now forced to be the identity element. It's still there, but it's the identity element. So I can just throw it away. And what I'm doing is I'm multiplying all these guys by H, and multiplying this all by H, I can just bring these things together at, I'm trying to multiply the outside of this thing by H, and I can think of it as being geometrically getting rid of those things and wrapping H all the way around it. It's equivalent. Okay? Does that make sense? Yeah. So let me back.
Sorry, the row can only be unitary. You cannot.
Yes, they have to be unitary. They have to be unitary, irreducible representations. That's right. Yeah. So, let's see. Yeah. So here, I mean, at this point, we've almost got the whole thing done. That we fix the these edges along the top, and that fixes all the conjugacy classes. And we're fixing the representation in the plaquettes, and that fixes, the representation value here. There are two indices to these wave functions. One of the indices is not going to be disturbed by that last plaquette operator. One of the indices will be disturbed by that last plaquette operator. So the one that's not disturbed is the vector that you have to define along with the representation. So when you pick a representation for a plaquette, you have to pick a vector, and the index which is not disturbed by the last plaquette is that vector. And then there's one additional index, and that's going to give you the topological degeneracy. Okay, so let me. Okay, so now we know how this last plaquette operator acts on these basis states. It's a rather simple way, and all we have to do now is decompose this action into the irreducible representations of that last plaquette, and then we're done. Okay, so maybe I won't go through the details of how that happens. And I guess the thing that's non-trivial is how counting of the different fusion channels ends up reproducing the counting of fusion channels in the quantum double. So that's the thing that's a little bit non-trivial. But if you want to actually generate the eigen wave functions, this is all you need to know, that I've fixed all the conjugacy classes, I've fixed all the representations. I know how this I have only this one last plaquette operator that I have to apply. I use this one last plaquette operator, and it makes some transformation on the basis that I defined, which has a fixed energy, and then I just have to decompose that into the irreducible representations, and that lines up with the final plaquette. And then it's done. Then we have the whole wave function for every single eigenstate of the system. Okay. Maybe it's gotten too obtuse at this time. So I see that a lot of people have tuned out. So it seems like maybe I've lost a lot of the audience. Because I gave it my best try. Apologize. But I can choose to stop there if it seems to. Go ahead.
Oh, sorry, I didn't have a question. Go ahead.
Okay, so we can maybe have a vote. One possibility is I can declare that that's the solution at that point. The other possibility is I can actually describe how this lines up with the representation theory of the quantum double, because somewhere in the counting of states, I had to do fusion of a whole bunch of objects within the quantum double to count states. And so far, I haven't said anything about the quantum double.
Okay, yeah, I think it's up to you, Steve.
Yeah. So I don't know.
Maybe, yeah.
I'm happy to stop there because I sort of gave the the general idea of what the solution is, and that was kind of the most important part. And I also gave you what the main trick is. So I'm happy to stop there. I've been going for an hour and a half now, and it's maybe not fair to take up more time. But if anyone's particularly interested, maybe they can feel free to. I can answer questions further if people want to.
Sure. I mean, yeah, that's fine too. I guess maybe maybe people can ask questions following.
Yeah, maybe we go on to questions at this point. Okay.
Okay. Yeah, but I would say let's.
Okay.
Thanks, Steve, for this nice talk.
Okay.
Thanks.
Thank you. All right. Yay.
Yeah, I guess yeah.
Okay.
Anyone who has questions, feel free to to ask.
Okay, there's at least one question. So go ahead. Yeah.
No, sorry, was mistake. But no.
Okay.
Okay.
All right.
No, but that's still true because I have questions.
Okay, go ahead.
Yeah, so I guess this may be related to what you didn't talk, because you said at the beginning or during the middle of your talk, like the dyons are not eigenstates of the Hamiltonian, are not necessarily
That's right.
the eigenstates of the Hamiltonian.
That's right.
So it seems like from your picture, you know, the eigenstates are spanned by you know, fluxes and charges.
Only fluxes and charges. That's right. Yes, that's right. The eigenstates
Right.
are completely spanned by fluxes, pure fluxes, and pure charges only.
Right, but you know, but because you know you're like I guess in your model, the charges lives on plaquette, and then the fluxes live on the vertices, and then if I choose a pair of you know, a vertex and a plaquette which are adjacent, right? Then I put the flux in the vertex and the charge in the plaquette, then they seem to form a dion, except I can't see the quantity class there.
Yeah.
Can you say
Yeah.
something
So that's the sort of interesting thing. The energy eigenstates are still classified by only looking at pretending they just didn't see. They're commuting projectors, right? They have to be completely independent. That you can set each of them completely independently. This is sort of the surprise. I don't know. I was taught or I learned this from a bunch of papers, and I thought, okay, if you have a vertex next to a plaquette, I should be thinking in terms of dyons. But if you're looking at the energy eigenstate, you shouldn't be. You're looking at pure fluxes and pure charges, and that completely spans the spectrum.
Mm-hmm. So are you saying that if I have a flux and I have a vertex near to each other, then that can be decomposed maybe as a superposition of the actual dyons in terms of quantity classes?
That's right. That's right. I mean, and there's I mean, actually this other group by where I showed you their paper earlier. They discuss in some detail about which you know, which fluxes and charges have to combine together in what ways to create the eigendyons. So they actually have that you know, the what do you call it? The way the group breaks up, you know, the way that the structure breaks up, that these two fluxes and charges have to combine together in this sort of way to make this eigendyon. And these two dyons have to get together in this sort of way to construct the eigenenergies.
Mm-hmm. I see. Okay.
Yeah, it's really
thanks.
it's quite surprising. But I mean, the only place in the entire calculation that I've done, the only place you need to know that there are dyons is when you then try to fuse everything together, is when you're putting the last plaquette and you're asking how many fusion channels are there over the entire system. So there you're fusing within the entire group, within the entire quantum double, and the dyons are generated in that fusion product, and you need to know what the entire fusion relations are, which includes dyons. But that's the only place where the dyons actually appear explicitly.
I see. Okay. Yeah, that's great to know.
Yeah.
I guess lots of people have to leave early because they have some other matters.
That's quite fine. You know, it's I totally understand. Yeah.
Yeah, but maybe I just want to check. Are there any? Do other people have any questions?
No others?
Okay, I'm gonna stop the recording now.